Okay, welcome back to part 2. Just so you know, my class is present, so I may have to yell at them. All right, so we yesterday got up through question number 2, but I want to go back and point out some errors that I made because I do that all the time. And for the kids in my class, I want you to pay attention because when I went over the other day, I made an error as well. A couple of errors, actually. Errors that I'm kind of embarrassed about a little bit. All right, so first things first, when we did this problem in class, we just multiplied by 22.7 cubic decimeters. But remember, that's the volume at STP. So one thing I noticed when I was doing the video yesterday, it says SATP. So I noticed that there were 2 marks, and I was like, just this math is not sufficient for 1 mark. So why'd they tell us section 1? Because what we have to do is actually figure out the volume at SATP. So in the data booklet, it tells us the pressure is 100 kPas. So I just solved for the volume of 1 mole, but the only thing different is the temperature of 298, and I got 24.8. So I just replaced that and that. That also changed this, but the process is still the same. Everything looks good down there. Okay, so down here in problem number 2A, part 2, we had to do the percent error, or the percent uncertainty. Look what I did. Look what I did here, kids. 0.5 plus 0.5, I said equaled 0.1. It doesn't equal 0.1, it equals 1. So we got to replace that. I'm going to resolve it right now. All right, so 35,100, well, you don't need to see the calculator, times 0.02 over 100 plus 1 over 21, and I get 1,673. Right, so it's 1,673 joules. So we change this to 1673. So let's 1673. Thousand equals times 100, not 1,000. 100 equals 4.77%. 4.77%. So you can see how really easy to make a little error like that. But at the rate I was going through it, I would have had time to go back and check. Does that mean you actually got it correct? Nice. All right, so that's pretty much it. I think we good. I did make a couple of weird little errors, but yeah, I think it's probably good. All right, so moving right along. Question number 3, and this is, I think we did this in class, right? Well, whatever. It says hydrogen is manufactured from methane by a process called steam reforming. So we got the equation here, and it gives us a delta H value. Please note that the delta H value is positive, which means that the reaction is endothermic, which means that heat is a reactant. All right, so it's deduce the equilibrium constant for the reaction. So remember, it's products raised to the power of their coefficients over reactants. So in this case, Kc will be equal to the concentration of carbon monoxide times the concentration of hydrogen cubed divided by the concentration of methane times the concentration of water. Now everything is a gas here. Remember, you can't put in liquid or solid, just gas and aqueous, but since everything is a gas, that's perfectly okay. Predict with a reason the effect of increasing temperature. Well, if you increase temperature, you add heat, right? So I would say, hey, by the way, kids, if I'm off screen, let me know. It favors the forward reaction. And if it says predict with a reason, I would just say for the reason, you could probably just say it's an endothermic reaction. If you wanted to be sure, you could describe like the motion of the particles, increasing the temperature makes them move faster, they collide more, blah, blah, blah. But I think because it just says predict with a reason, that is the reason, because it's endothermic. Yeah, I mean, that would be fine as well. All right, part C says explain why the reaction rate increases with temperature, adding annotations to the following Maxwell-Boltzmann graph. All right, so one thing you have to know, that since the x-axis is kinetic energy and activation energy is the amount of kinetic energy needed for a successful collision, I would just annotate a line on there and label it activation energy. Or you could just label it E sub A, because that's the notation. All right, so when I explain, I'm going to say, what I'll do is like maybe shade that in vertical and shade that in diagonal, right? Or I would say maybe I'm just trying to say I would show it. I would say like this region right here is the kinetic energy, the lower thing. Man, it's harder to make a video on my class present. All right, so I would just say in the warmer curve, you know what I would actually probably do? Label one like T1 and the other T2. That way you could just refer to T1 or T2. Anyway, but if T1 would be the warmer curve, in the warmer curve, you have more particles that have sufficient energy, or words to that effect. Now that's 3 marks, right? So I got my activation energy, I got my annotations and the explanation. I think that's good. Part D here says annotate the Maxwell-Boltzmann distribution graph to show the effect of a catalyst. Well, this vertical line represents activation energy. Since the catalyst lowers activation energy, this vertical line would be the activation energy with the catalyst. Pretty sure that's going to get the 4 marks, but only one way to find out, and I won't find out until the fall. All right, part E says the reactants, methane and water, now this we did not do, are passed over nickel. The following mechanism is proposed. So we see here in the first step, which we're told is the rate determining step, we have methane and nickel. Now, since we added nickel, notice how it does not appear in the overall equation. Since it was something we added to the reaction and it's not part of the overall equation, that means it is acting as a catalyst. Remember, an intermediate is something that's produced in a step and consumed in another step, but a catalyst is different. We put it in there, but it itself doesn't change. So the reason I would say we added it, but it is not part of the equation. Thanks for letting me know I was off screen, by the way. All right, deduce the rate equation. Well, super, because if the rate determining step is the, thank you, if the rate determining step is the slow step, I want to be like zoomed appropriately too, you know what I mean? All right, if the rate determining step is the first step, then the order with respect to each reactant is just the coefficient on those reactants. So since all I see is methane here, I would say that the rate is equal to the rate constant, whatever it is, times the concentration of methane. Would have been more challenging if the rate determining step were further down. Easy peasy lemon squeezy. All right, so the next part says, suggest why experimental confirmation of this rate equation would not prove the mechanism is correct. Yeah, you know what I would say? It's the same reaction here, right? So I would say our Kc expression, or you could just say the equilibrium constant expression, shows that changing, I'm gonna annotate here with square brackets, the concentration of steam has an effect on the rate of the forward reaction. Now again, this is one of those, or words to that effect, but does my reasoning make sense? Yeah, okay. Sketch a graph of the relationship between the rate and the concentration. So this is rate over concentration. As we move right to left in the x-axis, we're increasing concentration. Well, what happens to rate if you increase concentration, it goes up, right? Now, because of this rate law or rate equation, we know it's first order. That means doubling rate, doubling concentration doubles the rate. That's a directly proportional relationship. So you should have a graph that looks something like that, and it would have the equation y equals x.
Do we need to set the equation?
No.
Okay.
I would, if like, for me, I mean, I didn't label the axes. I don't know how strict they're going to be about the perfection of your sketched graph. So I just wrote the equation there I would write it there just to be like, yo, that's the equation for that graph if it's not drawn perfectly. By the way, did you guys have rulers?
No.
I say it every year. The kids need rulers. I've been saying it for 8 years, so no need to say it.
Yeah.
Next year I'll make sure. Because sometimes you have to like do a line of best fit and calculate the slope of it. IB Chem needs a ruler, but I'll talk to the coordinator. I got no complaints about her otherwise, so I'll be nice. All right, calculate the standard entropy change of the forward reaction in joules per Kelvin. So here we got the reaction again. Use section 12 of the data booklet. All right, so let's go ahead and I gotta open up my IB. I got the cords all over my computer here. IB chemistry data booklet. Yeah. All right, so table 12, you'll probably recall, is enthalpy of formation. When it's enthalpy of formation, it's the enthalpy, the sum of the enthalpy of formations of all the products minus the sum of the enthalpies of formation of the reactants.
Entropy, right?
Well, yeah, enthalpy gives free energy. It all works the same. You know I make those kind of errors when I make videos. It's impossible for me not to. And I also do things like 0.5 plus 0.5 equals 0.1. All right, so there's our data booklet. Let's go back to the test so we can see what we're looking at. All right, so calculate the standard entropy change. It gives us the entropy of hydrogen because it's not in the data booklet. So when I stop texting me. All right, so it's going to be the overall entropy change of the reaction is the sum of the entropy values for the products minus the sum of the entropy values for the reactants. Jesus, what is going on here? Who are you texting me over and over and over again? All right. So our products are carbon monoxide and hydrogen. We got to follow the coefficients. So this will be 3 times the entropy of hydrogen, which is 130.7, plus the entropy of carbon monoxide. Help me, kids. Carbon monoxide. There it is. 197.7. Is that what that says?
Yeah, 197.
Thank you. 197.7. And then minus the sum of the entropies of the reactants. So methane is right at the top, I remember. And that's 186. Plus gaseous water, which we call steam, which is 188.8. When you do the math in your calculating machine, 3 times 130.7 plus 197.7 minus 186 plus 188.8, I get positive 385 joules per Kelvin. And let me actually go back to my test. All right, part G says calculate the Gibbs free energy and the equilibrium constant for the forward reaction at 1500 Kelvin. Use sections 1 and 2. All right, so if we know the value for K, if you're unable to answer, I haven't looked at this in advance, so let me just, let's look at the data booklet, because I don't think we have a value for K, right? So we can't use delta G equals RT times. Do we have a delta H? We do. We've got delta H, we got the temperature, and we got the delta S. That tells me we can calculate delta G using delta H minus T delta S. All right. So delta H was a 206 minus the temperature, which is 1500 Kelvin. times the entropy. Remember, that's in joules. That's in kilojoules. So we got to divide by 1,000. So times 0.385. When I punch the values into my calculator, 206 minus 1,500 times 0.385, I get negative 371.5. 3 sig figs there, so I'm going to make that negative 372 kilojoules per mole. All right, part H says determine the temperature in Kelvin at which the forward reaction becomes spontaneous. So remember, since delta G negative means spontaneous and delta G positive means not, delta G would be equal to 0. So 0 equals delta H minus T delta S. All right, so if we're going to solve for temperature, then temperature will be equal to, let's see, well, I'm going to subtract this factor from the other side to make it positive, and then it's going to be delta H divided by delta S. Easy peasy lemon squeezy. Yeah, so the delta H is 206. Delta S is, where is it? 0.385, right? Yeah, 385. So 206 divided by 0.385 equals 535 Kelvin. Well, you'll find out. All right, on to number 4. The water-gas shift reaction is another way to manufacture hydrogen. State the oxidation state of carbon in carbon monoxide and carbon dioxide. Easy, easy, easy. So in carbon monoxide, it's CO. Oxygen is -2, so carbon's +2 there, +2. Remember, you have to write the oxidation state as +2. If you wrote it as 2+, they're not going to give you the mark. Stupid, I know, but it is what it is. All right, and in carbon dioxide, there's 2 oxygens, so we have 4 units of negative charge. So carbon here must be +4. Identify the oxidized and reducing agents and the species oxidized and reduced. All right, so if carbon monoxide, carbon is +2, and in carbon dioxide, it's +4, that means carbon was oxidized, which makes, if carbon is oxidized, that makes carbon monoxide the reducing agent. The species that was oxidized is just carbon, not CO. I don't know if they're going to make that distinction. Now here, hydrogen in water is +1, and in its elemental form is 0. So hydrogen was reduced, right? So that makes water the oxidizing agent, and the element that was reduced was hydrogen. Draw the Lewis structure of carbon dioxide. I mean, you could go through the steps, but I'd be willing to bet a lot of you guys could just draw this one from memory. Annotate the Lewis structure in here to show the polarity of the bonds by adding the symbols delta plus and delta negative. Well, remember, the oxygen is more electronegative than carbon, so I'd have a delta negative there, a delta negative there, and the carbon is +4, right? So delta positive there. Explain the molecular geometry and the polarity. All right, so the geometry,
Wouldn't it be delta negative on both sides?
I did. Oh yeah, I'm sorry. I didn't. Yes. My bad. It's hard to, when you have this ADHD brain, it's really hard to notice when you make an error like that. That's why I went back and corrected the things I did yesterday. Just because I don't want, I can't have comments on there, which is good because I'd have a bunch of comments saying, you dumbass, like 0.1, you know, you get the idea. All right, so I'd say the geometry is linear. The explanation for that, I'd say 2 electron domains, no lone pair or bonding electrons on the central carbon. That explains the geometry. The polarity, I would say it's non-polar because the dipole moments cancel out. And if you describe like why they cancel out, equal and opposite vectors, things like that, great, but you probably didn't have to. All right, going on with question 4. It says state the hybridization of the carbon atom in carbon monoxide and carbon dioxide. Well, guess what? In both cases, it's sp. Because this is carbon monoxide, and we drew carbon dioxide here. There's 2 domains around carbon. 2 domains means sp. 2 domains around carbon means sp. State the number of sigma pi bonds in carbon monoxide. Well, remember, the first bond is sigma, the others are pi, so 1 sigma and 2 pi. Determine the bond enthalpy of carbon monoxide in kilojoules per mole using section 11. Ooh, determine the bond enthalpy. They made this one just a teeny tiny little bit harder. So when we do bond enthalpy, delta H is the sum of all the bond enthalpies of the reactants. I'm going to say BE react minus the sum of all the bond enthalpies of the products. All right, so here we are given the enthalpy of formation. Determine the bond enthalpy of carbon monoxide. All right, so when we set this up, we know, oh, this is, I don't know, do we need that delta H value? Probably not. All right, so anyways, let's go to our data booklet. I'm going to pause the video and do all the work, and then I'll put it back up just to reduce the time of the video.
I do remember that.
Yeah. All right, so when you do the math, you get that the delta H value is 1,077 kilojoules per mole. All right, young ones, I'm recording here. I'm recording, just so you knows. All right, successive ionization energies of element E are shown. E is not the real symbol of the element. Identify the group of the periodic table. So we got to look for that big jump. So we see 1,000 to 2,300 to 33 to 45, 6. Oh, we don't get a big jump until after the 7th. What that means is that this element can lose 7 electrons before it has its full noble gas electron configuration. So what I want to do is just count backwards. So 1, 2, 3, 4, 5, 6, 7. Ooh, manganese could lose 1, 2, 3, 4, 5, 6, 7 electrons before it gets its noble gas configuration. Yeah. So manganese is in group 7. So group 7. Remember, hold your questions. If you have any questions, save them for the end. All right. And the reason I would say that E loses 7 electrons before large jump in ionization energy. I'm rushing here if you couldn't tell. All right, I'll pause. Sure. Yeah, my kids corrected me. It'd be group 6 because it loses 6. So for manganese, the 8th ionization energy would be the high one. All right, so moving right along. Element E forms an oxide, EO3. 2 possible Lewis structures are shown. All right, so here we got to do formal charge. 2 calculations. The formal charge for each element is the number of valence electrons minus the number of bonds coming from the element minus the number of non-bonding electrons. And then to get the formal charge for the whole compound is the change in formal charge is just the maximum minus the minimum. So let's go ahead for structure 1. In structure 1, I need my reading glasses here. Because yeah, the dots that bled through. So let's do for this oxygen on the left. We'll call it oxygen number 1. Oxygen has 6 valence electrons. There's 2 pairs in there, so 2 bonds coming out of it. And there's 4 non-bonding electrons on it. 6 minus 2 is 4, minus 4 is 0. For the second oxygen, I'll call it oxygen 2, 6 valence electrons. There's only 1 bond because there are 2 electrons coming out of it. And 6 non-bonding electrons. So 6 minus 1 is 5. 5 minus 6 is negative 1. And for the third oxygen, it's the same as the second, so the third is minus 1. So for structure 1, I'll say for structure 1, are we running here? Yeah, we are. Max minus min, the min is -1, the max is 0, -1 minus 0 is -1. All right, for structure 2, we're going to do the same thing. I'll start with the oxygen over to the left. I'll call that oxygen number 1. That's all going to be structure number 2. That's going to be 6 valence electrons minus 2 bonds minus 4 non-bonding electrons, same as this one up here. This oxygen is also the same, right? Because 2 bonds, everything the same. That one's the same. Ooh, so structure 2, all the formal charges are 0. Add them all up, max minus min, you get 0. Whichever one's closest to 0 is preferred, so structure 2 is preferred. All right, write the balanced equation for the reaction of EO3 with water. Well, in order to do that, first of all, we know that E is a metal, right? We know that much, right? Yeah. So when you react a metal oxide with water, it makes a base. But what we need to figure out is the oxidation state on E. Since oxygen is -2, E is +6. All right, so we're going to take EO3 and react it with water.
What's a bit off the screen?
Thank you, sir. So when we do the reaction, we're going to make a base, right? So we're going to make E hydroxide. We need this because we need to know how many hydroxide. It's going to be EOH6, right? And then balance creation reaction with water. Oh, just that. Sorry. All right, so since there's 6 of those, I need 6 of waters, and I believe that balances it, doesn't it? Yeah. So if it was Na2O, sodium oxide, it would be sodium hydroxide, right? So you're going to make E hydroxide, and we get the 6 there. All right. Part C says a strong acid was titrated with 0.01 molar ammonia. The pH curve is shown. Identify the best indicator using section 22. So when we scroll down to 22, that's our acid-base indicators. We want an indicator that changes within the equivalence point, right? And it's got to be within one of the pKa for the acid or pKb for the base. All right, so if we look at our graph here again, it was a strong acid titrated with a weak base. So the equivalence point is right in the middle of the linear region. So it's about, like, changes around 5 or 6, right? So I'm going to want to choose an indicator that changes color in that range. So methyl red would work. Really? You know what? I think methyl red is the only one they're looking for here. I could be wrong, but so I would say methyl red. Use the best indicator. It doesn't ask for a suggestion, so move on. All right. Sketch the following graph. Sketch on the following graph the curve expected if 0.01 molar sodium hydroxide was used instead of the ammonia. So all this would stay the same. But you see how this pH is slightly acidic? That's because we titrated a strong acid with a weak base, and the conjugate acid of that weak base is acidic, right? But sodium hydroxide is a strong base. So one difference, you're pretty much going to get the same general shape here, but maybe a less gradual rise. Now for your linear region, you want to make sure that the end point is right at 7. So since I started this at about 3.5, I'm going to go up here. So like I should have actually, you know what, I'm going to make this go a little bit steeper. Since I started it at 6, I'm going to make this go to 8. And then you're going to make it end at a higher pH. Jesus, that was terrible. So what you want is a less gradual rise, a higher equivalence point, and a higher end point. Man, that was much better in my mind. All right, determine the relative atomic mass from this mass spectrum. All right, so this is easy. Remember the mass spec gives us the mass of each isotope. The height of the peak gives us its abundance. They gave you the abundances so you didn't have to measure. So when I'm calculating the relative atomic mass, that was going to be an A, not a triangle. Thank you, sir. I guess you can see the paper. So the first one is mass number 58. Abundance is 0.68. Plus the next one, which is 60, times its abundance, which is 26% or 0.26. Plus the next one, which is 61, times its abundance, which is 0.01. Plus the next one, which is 62, times its abundance, which will be 0.04. Plus the last one, which is 64, times its abundance, which is 0.01. All we got to do now is plug it into our calculator. Let me pause real quick. Okay, so when you do the math, you get 58.77. I screwed up putting it into my calculator at first. I got like 1600. I knew that wasn't right because my answer needed to be between 58 and 64. It should be closest to 58 since you have the greatest amount of that isotope. Deduce the nuclear symbol for an ion of nickel with 58 with 26 electrons. So if it's nickel 58, yay, the atomic number of nickel is 28, right? And if it has 26 electrons, that means it lost 2, so it would have a charge of 2+. What's that?
That's pretty good. I felt good.
I mean, I would hope so. My Chem 1 kid should feel good about that one.
Yeah.
All right, draw arrows to represent the electrons in the orbital diagram for this ion. So remember, if nickel loses 2 electrons, the first electrons come from the 4s. It lost 2 in total, so it lost both of those 4s electrons. Nickel is at 3d, 1, 2, 3, 4, 5, 6, 7, 8. So it'll just be 1, 2, 3, 4, 5, 6, 7, 8.
Okay.
Predict giving a reason whether it's para or diametic. It's diametic. Diamagnetic. I can't even say this. And the reason? Because it has unpaired electrons in 3D.
I think I said that.
Diamagnetic means it is attracted to. All right, so anyways, let's move on.
Confused because there were some that were paired but some that were unpaired.
All you need is some unpaired. Like, you know, how we use iron for magnets, right? Iron is a really good magnet because it has 5 unpaired. Right, so the strength of a magnet can change depending on the number of unpaired electrons.
Okay.
But all you need is unpaired electrons to make it work as a magnet. All right, moving along. Explain. I'd like to work these out beforehand, but I guess doing it this way gives you my train of thought. Nickel forms a green complex. Looks like with 6 water ligands and a +2 charge. Explain why with ammonia ligands it's blue-violet using section 15 and 17. All right, so what do we do here? We changed the ligand. Ligand was changed. Ligand. I just like to say the word ligand. Yes, ligand. Oh, come on. Give me my damn ligands. There's 17. Did we overshoot 15? No. All right, so really tiny. There's the spectrochemical series. Notice how there's ammonia, there's water. So the reason why, going back, ammonia is a stronger field ligand. If you just said stronger, I'm sure that's fine. Right? So that means it increases. I can't even think anymore. Why can't I think of the word? The splitting. Thank you, Jesus. The de-splitting. I don't know. Like, I need summer vacation really bad. All right, so explain using sections 15 and 16. All right, so I would say increased splitting. Means higher higher energy absorbed. I'm screwing up here because what I'm writing isn't making sense to me. Let me pause it. Okay, so my reasoning was actually sound. All right, so ammonia is a stronger field ligand, which increases the splitting among that D subshell. Now, increasing the splitting means a higher energy light is absorbed, or greater energy light is absorbed, and the complementary color is observed or reflected. So let's go ahead and look at our data booklet here and table 17, the color wheel. We're told that this complex looks green. To look green, you absorb red light, right? If we're told it looks blue-violet, let's just assume it's like in blue. That means it's absorbing higher energy light. So you see that higher. Okay, whatever. I'm moving on. I'm so sick of this curriculum. I know that's probably not going to change, but not the curriculum, just teaching in general. My brain is not what it was back in August, and I need those 2 months to recharge. All right, identify with a reason whether ammonia acts as a Lewis acid or Lewis base. It's going to act as a Lewis base, right? Because ligands are called ligands because they donate pairs of electrons. All right, next, we're almost done here, I think. Describe whether ammonia acts as a Bronsted-Lowry acid or base in the reaction with water. Include an equation. All right, so ammonia is NH3. All right, when you react it with water, since it's a weak base, it does have a reversible dissociation. You make ammonium ions and hydroxide ions. So ammonia, gains in H, right? Meaning ammonia is a Bronsted-Lowry base. Last page, yay. Oh my God, you kids are, anybody who didn't get this right, you're gonna kick yourself. All right, so remember I talked about the standard hydrogen electrode and I was like, you just gotta memorize this stuff. So this little tube, right, has our electrode. That electrode is made out of platinum. Right? Now, notice we have our electrolyte here. Our electrolyte is an acid solution. I'm going to say the concentration of hydrogen ions has to be 1 molar. Now, there's something leaving here. What leaves? Electrons. Right? And what goes in here? Well, it's the hydrogen fuel cell. So, hydrogen gas. You might want to say at 1 atmosphere. You don't need to, probably, as long as you said it's hydrogen gas. Formulate a cell diagram for the spontaneous reaction using phase boundaries. So, look at this. Our oxidation process is hydrogen being oxidized into hydrogen ions. Right? Well, guess what? What do you think happens at the anode? Those hydrogen ions are reduced back into gaseous hydrogen.
What is this copper complementary?
I'm looking at one here. A standard hydrogen electrode. Oh, thank you. So they're going to do a copper-2 nitrate half cell. Whoops. So the oxidation half equation will be hydrogen to hydrogen ions. So it'll be H2 to 2H plus, line notation, right? Then here, since this is going to be our cathode, copper ions are going to be reduced, right? If it's copper-2 nitrate, that means your copper-2 ions are getting reduced into solid copper, and there you go. And then finally, calculate the standard Gibbs free energy of the cell in kilojoules per mole using section 1 and 2 of the data booklet. Section 1 is going to give you the Nernst equation. Nernst goes to camp, right? So down here in topic 19, Nernst. Section 2 is going to give you Faraday's constant. All right, so let's go ahead and do this so we can be freaking done. This equation, the Nernst equation says delta G is equal to negative N F E theta, right? So we don't have the E theta value, but we can work that out. All right, so Then N is the number of moles of electrons. You can see here it's going to be 2 moles of electrons, right? I'm going to set this up down here because we got to figure out the E value, right? All right, so minus 2 moles of electrons times Faraday's constant, which I believe is 96,500. Yeah? Do you remember that? I don't remember. I guess I'll look. Yeah, I want to be actually right, though. Yeah, 96,500. So 96,500 times E theta. Well, E theta is just going to be the reduction potential minus the oxidation potential. Reduction potential for copper 2 to copper. We got to go to table 24 for this. Oh yeah, sections 1, 2, and 24. I'm like, why didn't it mention 24? But it did. So fast scroll. Faster. No, too fast. Next year's data booklet is fewer pages. All right, so copper 2 going over to, that's copper 1. Where are you, you bastard? Where's copper 2 to copper 1? It must be on the other side. Or copper 2 to copper. Copper 2 to copper. All right, it's plus 0.34. All right, so when we do this, it's going to be 0.34. I shouldn't have to tell you the potential for hydrogen is 0. All right, so our E value is just 0.34. All right, so it's going to be -2. Yeah, I get it. I get it. Negative. Come on now. -2. I need a new calculator. Times 96,500 times 0.34, and I get -65,620 joules. We're asked for kilojoules, so that'll be negative. Let's look at sig figs. There's a 2 only there, so I'm going to say -66 kilojoules per mole. Yay! Yay! All right, thanks everybody. I don't know that I'm going to do the paper 3. I think I'm IB chemmed out. Let's just take the rest of the year off, shall we?
Yes, absolutely.
All right.
I feel good about the paper 3.
Yeah, me too. All right. Hope everybody enjoyed and have a nice life.